5, 4, 3, 2, 1, 0. Lift off normal.
India's X-ray polarimetric satellite towards its destination.
So on 1st of January 2024, ISRO, or the Indian Space Research Organization, launched its first dedicated polarimetry mission called the XPoSat payload. This is India's dedicated space-based polarimetry observatory that will monitor high-energy astrophysical sources like black holes, active galactic nuclei, and pulsars. It was launched using India's flagship PSLV, or Polar Satellite Launched Vehicles, from Sriharikota, and will be placed at an altitude at about 650 kilometers. So in case you want to know a good scientific breakdown of the mission, you are at the right place. Hello everyone, this is Mayukh, an astronomy PhD student, and I make interesting content on space and astronomy. So without any further ado, let's dive in the video. Just a disclaimer, this video will have individual chapters going over each of the sections. I sort of highly recommend to stick through all of the chapters sequentially, as it will help you understand the concepts better. Let's talk about the primary science questions that the XPoSat payload is trying to address. First of all, it is trying to understand black holes. Black holes form when extremely massive stars run out of fuel and collapse due to its own gravity, forming a really dense and exotic object. The gravitational field of these objects are so high enough that even light cannot escape, which means a more technical way of defining a black hole is an object whose escape velocity is greater than the speed of light. And as we know, nothing in the universe can travel faster than the speed of light. So nothing can escape a black hole. The black hole has a lot of plasma and hot gas around it, and the exact mechanism of those radiations are still unknown. So this mission will try to address that. Second of all, it will also study active galactic nuclei, which, as the name suggests, are extremely bright central regions of a galaxy that is dominated by the light emitted by its dust and gas, which falls into its black hole. Thirdly, it will also study pulsars. Pulsars are extremely fast rotating neutron stars which have a very definite period of their own. And again, the exact emission mechanism of such exotic objects still needs to be understood well. This particular payload will be sensitive to the X-ray emission that is given off by these energetic sources in the range of 8 to 30 kilo electron volts. So as I've explained in my previous videos, different energetic processes in the universe correspond to different frequencies of light. Extremely high energy events like radiation around a supermassive black hole, or a supernova explosion, or active galactic nuclei always radiates off in high energy, high frequency waves, or the X-rays and gamma rays. On the other hand, diffuse structures like molecular clouds and galaxies as a whole sort of radiate off in the lower wavelength or radio waves. So what XPoSat is trying to do is it is trying to sort of study three main domains. Number one is the temporal or the time-related domain. That is, it is trying to understand the timing information of these high-energy astrophysical sources. Next, the spectral or the frequency-related studies, or how is the frequency signatures of the radiation varying from one place to the other within these systems. And third, and the most special, is it is trying to study the polarization, which corresponds to the orientation of the electric field within that particular wavelength. Okay, so in order to proceed further, we first need to understand about the concept of polarization of light. So light by itself is electromagnetic radiation, which emerges from the interaction of both electric and magnetic fields. So think of it in this way. If the electric field is oscillating in the Y direction and the magnetic field is oscillating in the Z direction as shown in this figure, then the direction of the propagation of light is actually in the X direction, which means that the light propagates in the direction perpendicular to the electric field and the magnetic field. And when it comes to polarization, the direction of polarization is actually directly dependent on the electric field vector of light. Depending on the nature of the light source or the direction of the light source, it may have different orientation of polarization. For example, the light can be vertically polarized, or the electric fields are oscillating in the vertical direction. It can be horizontally polarized, wherein the electric field or the polarization vector is oscillating in the horizontal direction as shown here. Or it could also be circularly polarized. Finally, there's also a fourth possibility where the polarization vector can have any arbitrary angle. In case of an actual astrophysical object, for example our sun, the net effect of all of these vectors combined together is actually zero, which means that direct sunlight does not have any net polarization. That is, all of the effects, all of the different vectors sort of cancel out each other over a certain period of time. However, if you have a polarizing filter, which is a special type of filter which blocks the direction of polarization of light, you can actually filter the sunlight, which in this case, if I passed unpolarized light through this particular filter, as you can see, it sort of removes out the other field vectors except the vertical one. Sunglasses often have polarizing filters in them, and it's sort of used to reduce the harsh intensity of the sun rays. Just like we have artificial polarizers here on Earth, there are naturally occurring polarizers within astronomical systems. For example, a giant molecular cloud has a lot of dust in them, and this dust actually acts as a polarizer. So imagine there is a background star which is giving out unpolarized light as shown in this image. Now what this dust will do is this dust will sort of absorb that particular light and re-emit that light in a certain polarized direction. In this case, this is the vertical direction. As you can see, this dust molecular cloud just acted as a polarizing filter. Similarly, polarization also plays an extremely crucial role in understanding the magnetic fields around highly energetic systems like black holes. Supermassive black holes sitting at the center of the galaxy has a lot of gas and dust surrounding them. Due to the strong gravitational pull of the black holes, this gas and dust starts swirling around them and starts accelerating. Eventually, it reaches high enough speeds within a significant fraction of the speed of light. And as a result, they turn into hot glowing plasma. Due to the presence of the magnetic field around such black holes, depending on the strength of the magnetic field, shape and path of the plasma sort of changes. If the magnetic field is weak, the plasma sort of drags them into a circular pattern. And as a result, when that plasma glows, it sort of gives a light which has a net polarization in the vertical direction, as you can see. On the other hand, extremely strong magnetic fields sort of resist the motion of this plasma, and in that case the plasma gives off a net horizontally polarized light, as you can see here. In reality, however, the magnetic fields which are in the stronger side sort of averages out both the effects, and you have a net spiraling polarization around such sources, as shown in this image by the Event Horizon Telescope. So all in all, as you can see, polarization plays an extremely crucial role in astronomy, basically trying to understand the magnetic field morphologies. Alright, with that out of the way, let's try to understand the domain of X-ray astronomy, especially in terms of space observatories. So to broadly classify, X-ray astronomy has four main aspects. The first aspect is the imaging aspect, that is, imaging this high energy X-ray sources. So for that, we have NASA's Chandra Space Telescope. Secondly is the timing aspect. So in order to understand certain phenomena in these transient sources, you need precise timing measurements, for which we have ISRO's AstroSat. Thirdly, the spectroscopy. So in order to get spectroscopy or frequency related information for the various wavelengths and energies given off by these high energy sources, we have Japan's Hitomi Space Observatory. Finally, the last missing piece of this puzzle was the polarization angle, which XPoSat is sort of bringing in and completing the overall picture. Now speaking about the actual payloads that is going to be a part of this mission. So first of all, we have the POLIX, or the X-ray polarimeter, which is the main instrument of this project. Next is XSPECT, which is an X-ray spectroscopy and timing payload. Okay, so let's try to understand what POLIX actually is. So POLIX is a Thomson scattering polarimeter. So a polarimeter is an instrument which is used to understand the polarization of light or coming off from a particular source. So this polarimeter is actually sensitive to the polarization given off by the X-ray photons. So the POLIX instrument is actually composed of the collimator, the scatterer, a base plate, and a detector. So a collimator is basically a device which narrows a beam of particles or waves so that it can become more aligned in one specific direction. So in this case, as you can see, the collimator inside POLIX is actually made out of hexagonal structures, which has sort of tapered holes in them. And due to this collimator, what happens is it restricts the view of the instrument to a 3x3 degree on the sky, as you can see here. And as a result, it just tries to study one particular object within this field of view and eliminates all of the background radiation coming in. The next part is the scatterer itself. So the scatterer is the circular looking object that is sitting right at the center of the payload, and this is made up of a low atomic mass material like lithium or beryllium. The function of the scatterer is such that it can perform anisotropic Thomson scattering. So what actually happens is, as these high energy X-ray photons sort of hits on the surface of the scatterer, it sort of vibrates and excites the free electrons within that scatterer and causes them to radiate anisotropically, which corresponds to a certain polarization of light. Okay, so next, coming to the detectors, we have the X-ray proportional counter detectors. And this particular detector is sort of made up of four main parts. One is the top plate. Next is the mylar window. Again, the top plate and the mylar window acts as a collimator, which sort of narrows the field of view for this instrument as well. Next, it has the wireframe. So the wireframe has all of the electrical readouts. Signals that the detectors are producing is being read out through this wireframe. And finally is the detector housing themselves. Now, what POLIX uses is an X-ray proportional counter detector. The way it works is, the detector output is directly proportional to the input radiation energy. So at its core, an X-ray proportional counter detector basically works by the following. Basically, it will have a chamber in which inert gas is filled in, and this inert gas gets ionized by the incident radiation. An ionizing particle entering the gas sort of collides with an atom of the inert gas and ionizes it to produce an electron and a positively charged ion, which is also commonly known as an ion pair. As the charged particles travels through the chamber, it leaves a trail of ion pair along its trajectory, the number of which is proportional to the energy of the particle if it is fully stopped within the gas. Now, in order to sort of stop the ions, we actually apply a high potential which causes a high electric field and sort of stops those fast moving ions. Typically, when a 1 MeV X-ray particle sort of enters, it will create about 30,000 ion pairs. So overall, how POLIX works is, as you have a high energy X-ray photon with a certain polarization coming in through the collimator and hitting the scatterer, which causes Thomson scattering, and that secondary photon is then read out by the detectors, which I just explained before. Alright, so the next instrument in the XPoSat payload is the XSPECT, or the X-ray spectroscopy and timing payload. This particular payload will be responsible for the spectroscopy and timing information. This will sort of attempt to record the fast timing information, which is extremely crucial in order to understand transient nature around these high energy black holes. It will also do that at a really good resolution. This particular instrument will be sensitive from 0.8 to 15 kilo electron volts. So at its core, XSPECT will have X-ray based CCD. Called the swept charge devices. Now, these are cutting edge CCDs which are actually used for high energy X-ray astronomy. CCDs, or charge coupled devices, are actually special semiconductor devices which are used in sensors of various instruments, including the digital cameras that we have, and as well as astronomical telescopes. The CCDs directly rely on photoelectric effect discovered by Einstein back in 1905. When a photon of sufficient energy hits that particular semiconductor devices, it knocks out an electron from it by the virtue of the photoelectric effect itself. And there's actually a thin layer of capacitor right below that semiconductor chip stores that released electrons. So in an ideal case, for one single high energy photon, there would be one single high energy electron. So eventually, overall, the CCD sensor as a whole breaks the image elements into pixels. Each pixel is then converted into an electrical charge whose intensity is related to the intensity of light that was captured by that particular pixel. So these CCDs can actually be used in the focal plane of this particular instrument in order to sort of study these high energy photons and eventually get a nice spectra out of this. Okay, so overall, XPoSat is a big victory for India, being its first ever dedicated polarimetry mission studying high energy X-ray sources like black holes and eventually enriching the astronomical community as a whole. So if you learned something informative from this video, please consider subscribing this channel as I make similar content, links to which can be found in the screen here. As always, I wish everyone a very happy new year, and I will catch you guys in the next one very soon.